Yeah, indeed. Okay, so first I'd like to thank Professor Wang for kind invitation to this conference. And so today I'll talk about my recent numerical studies on exotic defect structures in strongly confined chiral liquid crystals. This work was done with Professor Juma, and he kindly invited me to Ljubljana several times. Therefore, my work was supported so not only by Japan government, but also Slovenia agency and the Center of Excellence in Slovenia. And so this is the outline of my talk. So first I want to remind you what holistic blue phases are. Then I'll talk about my studies. So the first part is devoted to exotic structures found in my simulations. And the next part is devoted to the investigation of optical properties of these exotic structures. Now, first, let me talk briefly about holistic blue phases. And so Professor Kremer already talked about holistic blue phases. But again, let me remind you that so in a uniform nematics, the orientation of molecules look like this.
Just a stick. Use a stick.
Yeah. Thank you. Look like this. But so in a chiral liquid crystals, the director wants to take twist distortions, and if this twist distortion is along one direction, so this is called a single twist, and so this is the important ingredient of cholesteric liquid cholesteric phase or chiral nematic phase. But you can see that the orientation is uniform along this direction perpendicular to the twist direction. And then, we can think of a different configuration in which the director is twisted along all directions. So this is usually called double twist, and so this is the important part of cholesteric blue phases. And so directors cannot twist along this direction, and therefore this configuration is often called double twist cylinder. And so this double twist configuration is energetically more favorable than single twist because so this configuration so satisfies the so how to say so twist distortions also in more directions. But it is known that this configuration cannot fill in the whole space without introducing singularities, and thus so this is a kind of frustrated phase, and so this discrimination lines with winding number -1/2 inevitably appears in blue phases, and then how these discrimination lines and double cylinders are arranged in cholesteric blue phases. So this is the schematic illustration, and so in two cubic cholesteric blue phases, so these are arranged in a regular manner, and so in BP1, so the phase takes so body-centered cubic symmetry, and so in the other cubic phase, the symmetry is simple cubic. And so the lattice spacing is of the order of the wavelengths of visible light, and thus it shows Bragg reflections in the visible lens. That means so these blue phases shows color, so as shown in the right picture, photos. Due to the cubic nature of these phases, so the blue phases are optically isotropic, and in the bulk they show no birefringence. And so these interesting optical properties interested the physicists in 80s and 1980s and 1990s, and and also extensive studies have been done for acoustic blue phases.
Sorry, just a short question.
Yes.
If you take, for example, the right picture, why does it have this plate-like structure? Why does it have blue regions and green regions?
So you.
Is it due to different crystallizations of the?
Yes. So the Bragg reflections can also have different indices. So different colors also reflects different indices. And now, let me talk briefly about random theories, on which my numerical work is based. And also in random theories, the orientational order of liquid crystals is described by a second-rank tensor, and so in an isotropic phase, this tensor is so every component of this tensor is 0. But if it has a local orientational order, so some of the components are non-zero, and so it contains information about along which direction this the liquid crystal is aligned and how strong this orientational order is. Yeah, and the total free energy of this this system as a functional of this orientational tensor order parameter is given like this. So from the so now we are considering liquid crystals sandwiched by two surfaces, and there are two contributions, one from the bulk and one from the surface. And so in the following slide, I show you the results result of the configuration, so minimizing this free energy. Yeah, and the bulk part is composed of local part, and so this is the Landau expansion up to fourth order in the order parameter. Yeah, and the important thing is in a liquid crystal, so third order term is allowed, because a state with plus chi and a state with minus chi are not energetically equivalent. The plus chi and minus chi are depicted in these two figures, and so there's no reason for this state to have equal local free energy. That's why this cubic order term is allowed, and now this free energy density is already rescaled, and the one parameter here appears as a rescaled parameter, and so this corresponds to temperature. Yeah, and so this is the free energy density due to the inhomogeneity of the orientational order, and so this is again a random expansion up to second order in the order parameter, and also second order in the spatial derivative. Yeah, and so let me mention that so in this form, the first so we have first order terms in the spatial derivatives, so that is written like this. But so this term changes sign under inversion, and so this term is not allowed when inversion symmetry is retained. But now we are considering a chiral liquid crystal. So this term is allowed, and indeed this term plays an important role. And so in this rescaled form, so we have two rescaled parameters, and so one is the elastic. One is the elastic constant, but this is also regarded as the strength of chirality, and the other one, so eta is so just for simplicity to set to unity, and this corresponds to so-called one constant approximation.
So you both have these lengths here, so
Yeah. So in
Or
this.
2 pi or something like that.
Yeah. You're right. So in this form, the length is rescaled so that the corresponding pitches are now 4 pi. Yes. Yeah, and so now let me mention the surface anchoring energy, and so here I adopt a simple quadratic form, so with some value of the order parameters preferred by the confining surfaces, and so by choosing appropriate value of this chi s. We can model surfaces, say, with homeotropic anchoring or planar anchoring. And now, let me present some of my simulation results. So first, I want to present the results with results in the case of homeotropic anchoring. Yeah, so now I'm showing the structures found in my numerical calculations, and so here, red surfaces describe the location of discrimination lines, and the orientational order at the mid plane is also displayed, and so here, yes.
I just want to make sure I understand the numerics you've done. So you imposed your boundary, you took that Hamiltonian, and you numerically minimized the energy?
Yes, exactly.
And you did that over all possible configurations of the second rank tensor?
So I tried various initial conditions for the numerical relaxation, and also found these various structures.
But you're actually minimizing. The thing I was a little nervous about is I just want to make sure you did not assume that the pneumatic order parameter tensor is everywhere uniaxial.
In this case, so no uniaxiality is assumed in the calculation. So I mean, biaxialities are allowed in the calculation.
In the numerical calculation?
Yes.
Right. Okay. And then how do you identify destination lines?
So this is I identified them just by calculating the trace of the chi squared, and then so in the bulk pneumatic, chi squared is takes some value, and in the discrimination lines that value is a bit smaller. So then I'm just I'm just drawing
chi squared.
Yes, isosurfaces of chi squares.
I'm sorry, maybe you will mention this later, but within the plane, you apply periodic boundary conditions, right?
Periodic periodic boundary conditions are applied so along the lateral directions. Yeah.
Is there any special way you choose your x and y side lengths, or like the side
indeed. Yes. So when I try to find the configuration that minimizes the free energy, so I not only change vary the orientation order parameter, but also the size of the system. So that's the system. So in the numerical calculation, the correct periodicity can be found.
Okay, and then you take the side length for the free energy minimum.
Yes. Yeah, so in these calculations, I only changed two parameters. So one is the thickness of the cell, and the other is temperature. Just by changing these two parameters, I could obtain these various kinds of different structures. And so now this is the phase diagram in terms of cell thickness and temperature. And so here is the uniform line helix. So this is a like structure with a single twist. And the above is the normal alignment, without any particular structure. But so in between, depending on cell thickness and temperature, all of these 6 configurations find their stable region like this. and now so let me talk about a different case of so planar anchoring. And yeah, so in the case of planar anchoring, so when the cell thickness is incommensurate with the natural pitch of cholesteric liquid crystals, the system experiences some frustrations, as depicted here. And so how this so frustration is relaxed, so is given by this. So now, so we can find a so regular array of ring defects, or so in other cases, so we can find the double helix-like declination, but so it is a bit so distorted. Yeah, and again, so I'm also drawing a phase diagram in terms of cell thickness and temperatures. And so in the blue regions, just a simple cholesteric helix is so stable, but so in red and green regions, so these exotic structures are stable. And and also we can imagine that so when the cell thickness is 3/4 of the so natural pitch, the so frustration is expected to be so maximal, and the line of so cell thickness 3/4 of the so cholesteric pitch is like this. And indeed, along this line, the range of the temperature range of stable so these stable structures is so largest. And then yeah, so again, so this is attributed to the so highest degree of so frustrations along this line. Yeah, and so now let me focus on so this so structure with hexagonal symmetry. And so in this so structure, so you can find say double twist cylinder, like double twist orientation like this, and yeah, and yeah, so but yeah, this is again double twist, but it is also called Skamian excitations, and so Skamian excitation is also vortex-like excitation also in a vector field, and so then so this this structure can be regarded as a hexagonal lattice of skamions also in liquid crystals. Yeah, and so let me briefly describe so why so this kind of so hexagonal structure can happen so in this system. And so let me remind you again that so in the so Landau-Dujas free energy of the system, so we have a so cubic term, and so in the free space, so this is a so combination of three so Fourier modes, Fourier modes. So whose so wave numbers sum up to 0, and so in the bulk, so it is well known that so for the number of so these so combination of wave numbers to be so maximal, the so face-centered cubic structures in the reciprocal space is preferred, and so in the real space, so this is so body-centered cubics, and so this is the structure of phase 1, so possessing the symmetry of body-centered cubic. So, but so in our thin system, yeah, so we can only think of a combination of three wave vectors, so in a single plane, and so this is. And yeah, and so this is consistent with the observation of so hexagonal lattices in our system. Yeah, and so skamions are found also in diverse condensed matter systems, so including say two-dimensional electron gases or so some kinds of so Bose-Einstein condensates. So but so particular attention has been paid to the formation of skamion lattices in chiral ferromagnets, and so in 2006 6, there's a prediction of so square lattice over here of scattering excitations in a so chiral ferromagnet, and so in 2009 and 2010, so these hexagonal lattices of so scattering excitations are found experimentally. So in a thin film of so chiral ferromagnets. And the hexagonal lattice also in these so in these so chiral ferromagnets, and the hexagonal lattice also in our so liquid crystalline system so has so similarities so in that they are both hexagonal. So but so let me talk about some differences arising from the so symmetry of the order parameter. Yes, and as you know, so in liquid crystals, the order parameter has head-tail symmetry, and so this is a so scattering excitation. So in the absence of so head-tail so order parameters, so with head-tail distinction, and so this so skamion is so characterized by so pi over 2 rotation of the so orientational order, so from the center to the edge, and so when we want to so arrange so these so skamions so in a hexagonal manner, so we can just also place the defects of winding number, so -1/2, and so this is. Yeah, so again, so what we observed so in our simulations. Yeah, but also when we want to arrange the same so scattering excitations in a so in a spin system, so that distinguish also head and tail, so in the so order parameter. Yeah, it can be clearly seen that so introduction of domain walls is inevitable, and so this and that means that so hexagonal lattice of so this so these scattering excitations in a spin system is somewhat frustrated, and then so what kind of structures are possible so in spin systems? So this is I present them also in this page. So one is a square lattice of scattering excitations, and so in this case, also domain walls are absent, and so we just have to introduce also -1 defects also in the center of the system, and this is what also was discussed in a previous paper, so predicting so square lattice of scattering excitations. Yeah, and the other possibility is so plus Z skamions also in the sea of so blue so -z spins, and so in this case so we have no singularities also in this configuration, and this skamion is so characterized by so pi rotation of the order parameter, so from the center so to the edge, and this is so again what was observed so in actual so systems of so chiral ferromagnets. And now, so let me conclude the first part of my talk. So, and so by just also confining so chiral liquid crystals in a very thin cell, so we found various the possibility of various structure defect structures, including so skamion lattices, and so this is a skamion lattice, and so this is a ring defects, and yeah, and so I want to say that so liquid crystals can exhibit so much more exotic structures than as we already know or we can imagine. So this is the message of the first part of my talk. Yeah, and so now let me move on to the second part of my talk. So optical properties of liquid crystalline skamion lattice, and let me briefly mention the background of this study. So, so Dr. Jun-ichi is working with Professor Igor Musevich was interested in the possibility of scamming lattices, as we found, and then he started an experimental studies on the optical properties of a thin system of chiral liquid crystals, and then today I cannot give his results because I do not have his experimental materials. But I just want to say that his experimental study also motivated us to help him by calculating the optical properties of a thin system of liquid crystals. So here. The optical properties means how this liquid crystalline system respond to incident light. So say light is transmitted or light is reflected. And so now I have to skip all the details of the numerical calculations. But so again, I wanted to calculate the profile of the transmitted light and reflected light and the electric field. So inside the liquid crystal. So when light is incident, so normal to this normal to the liquid crystal, and we paid attention to the response of liquid crystal to the light with different polarization, and so we are dealing with chiral systems, so it should respond differently to lights with different polarization. So here left circular and right circular. Yeah, and again, so let me remind you that the length is now rescaled so that the natural characteristic pitch is 4 pi, and so in actual units, it is 160 nanometers. But so the actual value depends on material parameters, and so please just focus on the rescaling of the length. So in the following. Yeah, so now I'm plotting the reflectance of the liquid crystals as a function of the wavelength, and so here in glass, I mean that the liquid crystals are sandwiched by a thick substrate, a thick glass substrate, and so this lambda is the wavelength also in the glass. Yeah, and so this is the so here, so in red, so I show the response also to the left circular light, and so by green, so I plot the response also to right circular light. And so you can see that so as far as the reflectance is concerned, so the wavelength is longer, the response is so almost identical, and so only when the wavelength is shorter, so the response is distinguishable. And so now I'm showing you the so intensity profile of the reflected light. So at so this so wavelength, so in the next page. Yeah, so this is the the reflection intensities. So to the so left circular light and right circular light, and so in the left the intense the sorry. So the intensity profile so near the liquid crystal is plotted, and so in the right the distance distance of this plane so to the liquid crystal is also very large. And so just by looking at these figures, the intensity profile looks very similar. So, but so please pay attention to the scale of these two graphs. And so this is one order different in one order of magnitude. So that means so we have significant intensity difference between the response to left circular light and right circular right circular light. And next, so I'm plotting the response of so this profile with threefold symmetry to the light, and so again, so reflectance is plotted against the wavelength, and so now, so in contrast to the previous case, the response to the left circular light and right circular light are also clearly distinguishable. So for wider range of so wavelengths. And so in the next page, I'll plot the intensity profiles at so this so wavelength. Yeah, and again, so this is the intensity profile. So when the in the plane, so near the so liquid crystal, and so far away from the liquid crystal, and so now the intensity profile so for the left circular light and right circular light are so clearly so different, and so I hope so they are so distinguishable in experiments. And and finally, so the so one of the concern of so Andre Nietzsche was, so if so these two profiles are so possessing at least a threefold symmetry, so can be distinguished so by experiments. And so now I'm plotting the intensity profile. So when the the light is unpolarized, and so now so for the case of Skamion hexagonal lattice of Skamion excitation, so clear so hexagonal lattice can be found. But in this profile, so with threefold symmetry, the intensity profile is so clearly different so from that found so for the case of Skamion lattices. Yeah, so and again, I hope that so these so two profiles are so clearly distinguishable also in experiments. Yeah. Okay. Now, so let me conclude so my talk. And so in the second part, so optical properties of liquid crystalline Skamion lattice was so numerically calculated. And so we found that its intensity profile of reflected light so depends so strongly on the polarization of so incident light. So so here, so polarization means left circular or right circular. And so we also found that so these two liquid crystalline profiles are distinguishable so by the so intensity profile of so reflected light. Yeah, and also here, so I showed only some of my preliminary results, and so yeah, I know I should do some more so to so along this direction, and so probably so there are many things to be interpreted or so to be so discussed. Yeah, so but I hope that so yeah, so these so optical studies yes. So I hope that so these optical properties of thin films so chiral liquid crystals are interesting to you all. And so I still have so 5 minutes left, but so I know that all of you are very hungry, and yeah, now I stop my talk, and thank you very much for your kind attention.
Thank you. Perfect time. Very nice talk. Are there more questions? Yes, let me give you a microphone. It won't be good.
Thanks. I'd like to just bring you back to the early part of your talks when you explained that you write down the nematic energy in terms of your field chi. And I want, in terms of your chi field.
So you mean my explanation?
No, just your, if you can pull up
free energy, or just a moment.
Just the very early slide there, if you don't mind. I just have a specific question. If you want to write down in terms of your chi field the subtle splay term in nematic energy, how does it look like?
Is this fine?
Yes.
Is
it already there, or you know, like if you write the subtle splay?
So you mean the surface-like elastic term? So in
yeah,
this.
exactly. The volume one. How would it look like if you wrote it in terms of this guy?
So you're right. So to include the so surface-like term, so there's a possibility of adding an additional term. But so in this form, I just adopted this form, so presented in a famous review of right-hand marmins, and the possibility of the system being affected by additional so surface-like elasticity should be discussed. But I haven't done so I'm sorry.
More questions? Yes, Peter.
Could you maybe say a few more words about how you did the calculations for the reflected intensity?
Yeah. Okay, just. No. Just. Yes. Yeah, probably. So many people will rely on the famous finite FDTD method. But so in this work, I did not resort to FDTD method, and so I made a plane wave expansions in the lateral direction, and so along the normal direction, so in the liquid crystal, so I just assumed finite differences, this discretization. And so, am I answering your questions so properly?
How thick was your sample? How many wavelengths?
How many wavelengths? How many wavelengths? It's around 1. So this is a very thin sample. And the wavelength is of the order of this thickness.
So I was just wondering, experimentally, to test this experimentally, you'd have to actually put a camera right up within one cholesteric twist or less of the surface of your sample?
I hear from Andre that so he just measured the intensity profile of reflected light, and so as far as I understand, so he did not measure the intensity profile inside the liquid crystal. So but I have to ask
I'm just asking, is it practical to get that close to the surface, as close to the surface of the liquid crystal as you were doing in your numerical calculations?
Yeah, of course, yeah.
Because far away, you didn't see anything, right? If you're far away from the surface, if you're many wavelengths away from the surface, it just looks uniform, right?
So in this, so in this calculation, so you're right. So when the so when the intensity is measured so far away from the liquid crystal, so it's it's almost uniform. Yes.
So experimentally, can you get close enough?
I hope so. Yeah. Okay. But I guess I have to ask Andre.
Professor Choppage, do you have a comment or?
should see the far field diffraction pattern, but you should then look at the angular distribution, not positional, yes.
Oh,
There
yeah.
There should be a far field distribution. If you have a near field distribution, there should be a corresponding Fourier transform in the far field.
Yeah, but yeah, so you're right. So here, so I'm showing you so only the so near field response of the system, and yeah, so yeah, so for the so far field so intensity profile, so we know trivial. So the wavelength should be so smaller than the say the characteristics. So so lattice spacing of scattering excitations or the cell thickness. So it is again an experimental challenge.
Perhaps we can continue this discussion over lunch. Are there any other questions before we conclude? If not, I'd like to thank the speaker again.
Thank you very much.